we'll just quickly recap what we did last time. So we're talking about using integrals for area. Okay, using integrals for area, and we said there were two kind of main points that we had to address here. If we were going to do that, then we need to determine the rate of change of area, right? Because an integral expression, that function is a rate of change function. So if we're going to use integral to get something about area, then we need to know what is the rate of change of area. Okay, and the next thing was, then we need to investigate the impact on the integral value of intervals where the function value is negative, or if the function value is changing from negative to positive and negative to positive. What's that going to mean for this integral that's trying to compute, or we're trying to use it to compute area, okay? And so we took care of task 1, so let's just review that quickly. So determine rate of change of area, we looked at a constant function, right? We looked at a constant function like this. And we said, okay, as x increases, what is the rate of change of that area of that blue region? What is the rate of change of the area of that blue region? Yeah, so we determined that, we did some examples to show that it's 3, right? For every inch that x increases, our area is increasing by 3. For every 2 inches that width increases, the area increases by 6. For every ½ inch that the width increases, the area increases by 1.5. So that's indicating a constant rate of change of 3. So, and we said that the units of that was inches squared per inch, right? That change in area per change in width. And so then we noticed, well, that's just the value of the function. But then we also noted that it's a different unit. So that if this is inches by inches, then the units of that function would be inches. Or f might be just in some context, that might have a different unit. So it could really have any unit, pounds or temperature or something like that. Okay, but we're gonna just grab the value, right? The value of the function we know is the same as the value of the rate of change of that area, even though they have different units. We can still take hold of just the number, right? Say that they're the same. Well, then we said, well, what about if the function is changing, right? What if the function is changing? We looked at this. So as that function is changed, as x is changing and the function values are changing, how do we imagine that function if we want to try to think about the rate of change of this area as it's being swept out? What did we do or say about that? How are we going to imagine that function if we want to try to think about the rate of change of area sweeping out? Yeah. Yeah. So think about lots of tiny intervals where the function value is constant over each of those intervals. And so that's what happens when you zoom in on this. That's what you see, right? So if you zoom in. So this is the way we have a continuous curve, but we want to think of it this way. We want to think of tiny little intervals of constant function values. And that way we can relate it back to our first example of the constant function with constant rate of change. And so now we can say here, for this particular x value, that area is increasing at this rate, which is the value of the function, maybe 1.61 or something like that. And now 1.63. Okay, so let's look at, so the big takeaway from last class was that function values will give us the rate of change at that particular x value, the rate of change of how the area is increasing, or yeah, how the area is being swept out. The function value gives us that rate of change. So let's look at this example here. Nothing, not working. No. Is it my view? Yes, it is. Okay. All right, so here's a function f, and we're sweeping out the area between the curve and the x-axis. And so we decided, or kind of seen, that the values of that function can be our rate of change. So, before we do that, so we want to look at the impact of negative values of the function on the integral. So before we do that, let's just talk about so as x is changing here, how do you imagine the current value of the function, right? So where do you look, or what do you think about? So now x is increasing. What do you look at, or what are you thinking about in terms of identifying the current value of the function, meaning the value of the function for the current value of x? All right, so does the question make sense? What's that? Looks to the x-axis first. Yeah. No, I'm not talking about anything to do with accumulation of area or rate. All I'm talking about now is for the current value of x, which is the right side of the shaded region at the current value of x. How do you think about just the value of the function? Or where do you look for the value of the function? If it's okay, is it see if it's over or under the x-axis to see if it's positive? What about its value? Yeah. 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 So and then where do you look for that, or where do you see that? So let me just pause it on the y-axis. Okay. So if I pause it right now, how is the y value for this current value of x being shown or displayed? Meaning this one. So this is the current value of x right here. How's the y value being shown? What's that?
Isn't it just the curve?
The curve. The curve is the y value. What's that? It's the set of y values. Okay, so if you remember from maybe from an animation from the book, remember this? So I've added an arrow here. So what do you see that arrow is representing the current y value for the current value of x? Is that, you have a comment? Good. It's a vertical distance, right? It's a vertical distance from the x-axis to the curve. That's how we see the y value for the current value of x. Okay? And so then, what's different now than in the first part of the curve where it was green? Okay, so y values are negative, right? So when the curve is below the x-axis, y values are negative, and when it's above, y values are positive. So this is now if we're thinking about area and we're thinking about the function f being the rate of change, what impact are those negative values of the function going to have on integral? So for instance, this expression right here. So capital F of x is the integral from 1 to x f of t dt. So maybe just let's talk to the person next to you and explain, what is this function? What does it have to do with our conversation? What is it calculating? And then what's the impact of little f being positive here, and then little f being negative here? All right, so talk. So what's the meaning of that expression? What does it have to do with what we're talking about? And then what's the impact of little f being positive and then negative? Go. Yes, ma'am. Okay, net accumulation of the dependent variable. And in our case, we're talking, what were we going to say back there? Okay, signed area, what's that? So is it net accumulation of area? So if f is the rate, this area is sweeping out at a rate of little f, then why isn't this just the net accumulation of area? Okay, so function values here are what? Negative, right? We got our arrow pointing down, we got negative function values. So if we just look at, we know this is a net accumulation, then our function values here are all negative. So what overall contribution to the net accumulation are we going to have right now? It's going to be a decrease, right? Whenever f is negative, you're going to have a decrease, a contribution of decrease to the overall integral. So that's why we can't say this is an accumulation of just plain old area. Why? Because area is a positive quantity always. You can't really have negative area, okay? Area is always a positive quantity. But if we want to frame integrals in terms of area, then we can think about what's called signed area, which means we're going to allow for signed area to be positive or negative. Positive when the rate of change is positive. We're gonna sweep out a positive signed area when the rate of change is positive, and then whenever the rate of change is negative, we know the contribution to that integral will be decrease. So we're gonna say that we're gonna increase in negative signed area, or the signed area will go down, right? The signed area will decrease. Okay? Other questions or observations? So at this point, and you've already experienced that in your homework and the reading, so that should be familiar. Okay, so this idea of signed area, that's what net accumulation of area. It's not really net accumulation of area if you just have this single integral like this, 1 to x, and f is going through positive and negative values. We know that whenever f is negative, that's going to have a decreasing effect on the net accumulation. So that's why we're going to talk about signed area. Yeah, question?
You were saying, you were asking what, because they said that f of t is the rate of change.
Uh-huh.
So did we ever come to a conclusion of what it was of? Because you said what is
Yeah, okay, great. So great question. What is f of t the rate of change of? Area? Signed area, right? So it's the rate of change of the signed area because this is giving us net accumulation of signed area.
Okay.
Yeah. So that's the rate of change of signed area. When that rate of change is negative, our net accumulation is going down, right? So the total we're getting for function f, that's going to be going down whenever little f is negative. Yeah. Uh-huh. Yeah, so exactly. So what if little f was positive the whole way, then our signed area is truly an area. It's truly the area beneath the curve above the x-axis. Yeah. You just got to be sure that it's always positive. Then you can say, in that case, the signed area is the area below the curve above the x-axis. But if we ever have any part of our interval where that function is negative, then we have to use the term signed area. Other questions? Okay, so now I'm going to let this thing go. I'm going to show you some functions. So first these three. So I got a function p here, a function q, and a function r. All right, so I want you to identify what is p, what function is p, what function is q, and what function is r the rate of change of, right? So is it the rate of change of p or q or something else? So usually we use like r of, right? We put a subscript there, so r question mark. So with a partner, by observing the values as the animation plays out by observing the values. What is the function p? What is the function q? And what is r the rate of change of? What function is r the rate of change of? Is the task clear? So you're looking at the values as the animation sweeps out. Net accumulation of, what quantity is that? So net accumulation of signed area, right? So you should come up with Q as the net accumulation of signed area. So look, it's decreasing now, but still positive, and then at the end it turns negative. You see that? So it's increasing, 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 positive value. And where's its maximum? Right there. Now that net accumulation is decreasing until and then eventually it even becomes negative. Because the amount of area towards the end that's below the x-axis is greater than above. Okay, so that therefore that rate is the rate of change of which function? Is the rate of change of p, or is it the rate of change of q? I've heard most people say q. Rate of change of q. Right. Because it's the same as p, right? We said the rate of change, this is the rate of change of q, which we know is the value of the function, right? Is the value of the function, and they stay the same. Okay, I got two more functions for you. So now I want you to figure out what is the function g and what is the function h. And then I want you to write expressions for those. So if we were to write the expression, so we know p is f. If we were to write the expression for q, it would be, what is q of x? Let's practice that first. How would you write the expression for q of x? Integral from 1 to x? F of x? So can I use p? P of t dt. The net accumulation of signed area, right? Net accumulation of signed area underneath p. So we know the rate of change is p. All right, now, so you're going to identify what g and h are, and I want you to write expressions for those. Identify what g is, identify what h is, and write expressions for those functions. Go, figure it out. Logan, what'd you come up for g of x? Yeah, what did you think g of x was? So it's the net accumulation of area or signed area? Okay. But different than, how is it different than p?
Because that's just from it's only from 2 to 3.
Okay.
It's not like the whole thing.
So you want me to write from 2 to 3?
Yeah, because it goes from 2 to 3 of p of t.
What do we think? Agree? Okay, he wants from 2 to x. So some people are saying 2 to 3, some are saying 2 to x, some are saying that's the same thing, doesn't matter.
It's 2 to 3 because it stops, right?
Yeah, it stops.
So let's think about forget about the g of x. What about this expression right here? 2 to 3 pt dt. What's that? Why? Yeah. Right. So that would be what? It'd be the opposite of this gray area, right? 2 to 3 would be the negative version of, or the opposite of, that gray area once it's done. Right. It's right. This is, what is this? G of 3. This is G of 3. If we want G of x, then we need, so those who are thinking it should be 2 to x, We're correct, right? This is a function. It's the function of all net accumulation of signed areas starting from 2 and 2x, okay? And now, x can actually be less than 2, but the way I've shown it to you here, I'm saying x is only good if it's greater than 2, all right? Because I thought it might be a little confusing if I let x be numbers less than 2. It can, all right? X can be numbers less than 2, but I'm only showing you values of g when x is greater than 2, okay? All right, so this is another net accumulation of signed area, and it's always negative because the rate is always negative for this interval from 2 until 3. All values in between, right?
Professor,
Yes, please.
then how do you show that it stops at 3 on interval?
It's just my animation is stopping at 3.
Okay.
Yeah, so if we wanted, we could say 2 is less than or equal to x is less than or equal to 3 if we wanted just to say we're only interested in those x values. But really, the 3 is just about where my animation stops. Does that make sense? Yeah, so it's not really about, yeah. But if we wanted, then we could say let x only be the values between 2 and 3. Okay. All right, now what about h of x? What did you notice about h of x? Where's Miranda? Yeah. What did you notice about h of x? The integral from 0 to x, p of t dt. And why did you say that? Okay, so I'm hearing that you chose that 0 because the net accumulation of signed area was 0 where it started. Is that right? So is that a value of net accumulation of signed area? Right there. Is that what that is? Where's Jessica George? Hey, what do you think about what she said there? You agree with that?
If it's net, then would you
Start
start at 2 and not 0?
at 2. So h of x is net accumulation starting at 2.
Or no, don't do that.
What about 0? Is 0? Do you agree with 0? You think that this starts accumulating 0? What'd you notice about h? Okay, it's always positive. And then what? Did you notice anything else about h for low values? Anyone notice anything else about h? Just right now? Yeah, it's the same as q, right? It's the same as q until you get to 2, and then what happens? It keeps increasing, whereas q does what? How much does q go down by after we cross 2? After x crosses 2, how much does q go down by? And how much does h go up by? Anyone see it? What's that? Who said that? Yeah. And so, can you explain that?
Because it's rather than the signed area that it's accumulating,
Okay.
it's accumulating like the absolute value of all the area.
Okay. And what was g of n? G of n was tracking what? This negative signed area, right? Starting from 2. So really, doesn't q get some maximum value here, and then from there it goes down by the amount g? Right? And then after that maximum value, what does h do? It goes up by the positive amount of g, right? And so what about, so we need an expression for h. Expression for h. So, volunteer?
Sure.
Yeah.
The integral from 1 to
And why start at 1?
Starting at 1 because that's where our interval is starting for this animation.
Right, because we saw that it's the same as Q. It's the same as Q. It's the net accumulation of signed area starting from 1. That's what Q was. But then this one, when we get to these negative areas, keeps adding on area, right? So h of x is what kind of function? H of x is what kind of function? Right. H of x is our net accumulation of just pure area. Why? Because it adds on the values of g, but positive version, right? It adds on values of area sweeping to the right. So it adds on the opposite of g as it goes. So it's the net accumulation of area. Whereas Q was the net accumulation of signed area. Just the integral is going to track out signed area. But if we let that take the always positive version of the rate, right? So this is our rate function. If we make it always positive, then it's going to accumulate actual area, right? Yeah.
Is it wrong if it has the absolute value of the DTs within that absolute value?
Okay, let's see. So he's asking this. Is that still okay? So in principle, yes, it's fine because this is calculating a little bit. Think of it a little bit of area, or so. Yeah. So in principle, it's okay, but just conventionally, we don't include the dt in the absolute value. Okay. But yeah, in principle, it's the same thing. But we normally wouldn't write that. Okay, so now I want to take a look at any question.
When would it be different? When would it be different to include the entire thing in the absolute value?
Oh.
Good. You're moving backwards. Now you have a chance to multiply the negative with the dt by p before you take the absolute value, right?
Right. Yeah. So this is only good. This is only the same for increasing x. Yeah. Right. Okay. I want to show you my version of h of x, and I want you to make sense of it. So here's my version of h of x. So it's longer, not as succinct, maybe as I used f instead of p. So yours was this: 1 to x, what, f t dt, or p of t was the same thing. So I want you to look at this and make sense of why these two are the same thing. Go, talk. Why is my version of h the same as yours? So this is saying that when x is between 1 and 2, what is h of x? When x is between 1 and 2, h of x is? Just net accumulation of signed area, right? And so, since h of x is total area, that's okay because we know between 1 and 2, f is always positive. But then when x is greater than 2, what's the value of that function? Right, so what's the why h of 2? Why h of 2? Yeah, so that would be what we get in here if we plug 2 into this one. All the accumulated area, that's basically the area of the green region, right? Plus, now, we want to start accumulating from 2, but we want to take the opposite of the rate function to make sure that we're still accumulating positive area, right? Positive area. Yes, sir? Uh-huh. What? Right, but so yes, if x is 2, if x is greater than 2, we're gonna use this rule, which says plug 2 into h. So it doesn't. It's just plug 2 into h, which is gonna invoke this part of the rule and give you the integral from 1 to 2. Look, greater than or x is less than or equal to 2. Part of what h does is it takes your value of your independent variable, and it looks for which line to use. So if x is 2.7, it's going to come here, and it's going to put 2.7 in for x, and it's going to say, oh, first I got to get h of 2. And how do I get h of 2? Well, that's when x equals 2, and so that's going to invoke this. It's going to take the integral from 1 to 2 and find h of 2, and then it's going to go plus the integral from 2 to 2.7 of that. You see? So this is an x. So make sure that's not x. That's always 2. This is for values of x greater than 2. That's where that's going to go. Like a 2.7 or a 2.1 or a 3.8. But then that'll always be 2, not x. Is it better? Cool. Yeah. Okay, so again, should this be from 2 to 3? Oh, sorry.
No, I'm saying if x is
Yeah, so I suppose if we're just looking from 2 to 3, then yeah, you could say x is strictly greater than 2 and less or equal to 3. Okay, so for homework for Friday is going to be online homework through WebWork, but then there's going to be a written aspect to that as well that you're going to get from Blackboard, and here's the nature of that. Let me just show you the nature of that. Okay, we got a couple minutes left, so. Everything is going to be about definite integrals. So the written portion of this will be for you to do something like this. I'm going to ask you to interpret that in terms of a net accumulation function. So you're going to be writing out something like this. Now I want you to do this in your own words. So don't just take this from the video and then copy it. I want your own words. So here's what I'm looking for. This is a function value capital F of 2.4, where f of x is integral from 1 to x f of t dt. F gives the net accumulation of signed area for the graphed function f, little f. So f of 2.4 there is the net accumulation of signed area of f as x increases from 1 to 2.4. So, but I want you to do that in your own words, okay? Interpreting every one of these integrals as a particular value of a function that's a net accumulation function. Okay, does that make sense? But so and I'll put the exact instructions on Blackboard, and then I'll give you the. Most of you have used WebWork before, but there'll be also be a little primer on the WebWork system. Okay. All right. See you Friday.